The workshop in Izhevsk smelled of specialized oil and steel shavings. Winter light came through high windows, landing on a workbench where two rifles lay in careful parallel. Mikhail Kalashnikov, now in his early 40s, traced a finger along the longer barrel of the prototype. It was 1961, and the challenge before him was deceptively simple: create a light automatic weapon without creating anything entirely new. The AK-47 had proven itself across a decade of use. Its simplicity was legendary. 7 major components, tolerances so generous that environmental debris couldn't jam it. A gas system that functioned in temperatures from Siberian winters to tropical jungles. Infantry units carried it from East Berlin to Vladivostok. But tactical needs had evolved, and a gap had appeared in small unit operations. Squads needed sustained automatic capability. Not the short bursts of a standard rifle, nor the heavy, complex operation of a crew-served platform, but something in between. Something one individual could carry and operate. Something that could suppress an opposing position long enough for the team to maneuver. The existing solution, assigning one person to carry more magazines and fire longer bursts, was damaging equipment and creating logistics problems. Kalashnikov picked up the standard AK-47, feeling its familiar weight. Then he lifted the prototype, heavier, longer, but unmistakably part of the same lineage. The receiver was the same stamped steel. The bolt carrier, the gas piston, the trigger mechanism, all transferred directly from the design he had finalized 15 years earlier. Only the barrel, stock, and bipod marked it as different. He had been given strict parameters by the administration. The new equipment had to use the existing 7.622 39mm cartridge. It had to function with current ammunition production. It had to be maintainable by personnel with minimal training. And crucially, it had to integrate into existing supply chains without requiring dedicated infrastructure. These weren't suggestions. They were absolute constraints that would determine whether the design ever left the prototype stage. Kalashnikov set down the prototype and picked up a pencil, sketching modifications on technical paper. The barrel length would increase to 590 millimeters, long enough to maximize the effective range without making the equipment unwieldy. The receiver would be reinforced at stress points to handle the thermal load from sustained use. The stock would be fixed wood, providing stability for accurate automatic engagement from prone positions. What he was designing wasn't revolutionary, it was evolutionary, a precise adaptation of proven engineering to meet a specific tactical need. In this philosophy, equipment was a tool within a larger system, and the best tool was the one that fit seamlessly into what already existed. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far and stay with us for the next chapter. The pressure on Kalashnikov wasn't about innovation, it was about integration. The industrial complex was massive, standardized, and resistant to change. Factories in Izhevsk, Tula, and across the region produced AK-47s by the millions. Ammunition plants ran continuous shifts, manufacturing 7.62 39mm cartridges. Training programs had been built around the Kalashnikov platform. Introducing a completely new system would require retooling factories, retraining technicians, redesigning supply chains, and rewriting manuals. The request from the command had been specific: develop a squad-level automatic tool that minimizes industrial disruption. Kalashnikov understood what wasn't being said, that no matter how effective a new design might be, if it couldn't slot into existing infrastructure, it would never be adopted at scale. He had seen Western approaches to the same problem. The Belgian FN MAG, the American M60, both dedicated automatic platforms with quick-change barrels, belt feed systems, and complex mechanisms designed to sustain use indefinitely. They were impressive engineering achievements, but they were also separate platforms, requiring separate logistics, separate training, and separate maintenance protocols. Kalashnikov's insight was to ask a different question. Instead of, "How do we design the best light machine gun?" he asked, "How do we give an AK-47 the capability to function as one?" The distinction was subtle but crucial. It shifted the engineering challenge from innovation to adaptation. He began with the barrel. The AK-47's 415mm barrel was optimized for mobility. Extending it to 590mm would increase muzzle velocity, improve accuracy at range, and provide more surface area for heat dissipation. The longer barrel would also increase the gas pressure available to cycle the action, ensuring reliable function even when the equipment became hot and fouled. The stock required rethinking. The original stamped metal folding stock was excellent for portability, but provided insufficient stability for accurate, sustained fire. Kalashnikov designed a fixed wooden stock. Heavier, yes, but offering a solid cheek weld and shoulder contact that would keep the equipment steady. The wood also acted as an insulator, protecting the operator from thermal transfer. The bipod was a simple addition, a folding metal frame attached near the muzzle. When deployed, it transformed the firing characteristics, allowing accurate engagement from prone positions. When folded, it added minimal bulk and didn't interfere with movement. Magazine capacity presented a choice. The standard 30-round magazine would function, but wouldn't provide the sustained capability needed for a suppressive role. Kalashnikov developed a 40-round magazine as standard and adapted the tool to accept a 75-round drum for situations requiring maximum capacity. Critically, all three magazine types, 30, 40 and 75 round, were interchangeable and used the same feed mechanism. Each decision was a balance between capability and compatibility. The RPK emerging on his workbench wasn't pushing the boundaries of what these tools could do. It was finding the elegant minimum of what this specific tool needed to do within the existing industrial capacity. The mechanical logic of the RPK was the mechanical logic of the AK-47 extended. Kalashnikov wasn't redesigning the operating system. He was calibrating it for a different duty cycle. Understanding the equipment required understanding what stayed the same and why those specific elements changed. The gas operation system remained unchanged, a long-stroke piston connected directly to the bolt carrier. When a round functioned, propellant gases escaped through a port in the barrel, drove the piston backward, and cycled the action. The system was robust, heavy, simple, and tolerant of fouling. In the RPK, this durability became even more important. A standard rifle might fire in short bursts. A squad automatic tool would sustain use until the magazine emptied. The rotating bolt locked into the receiver through two lugs, the same mechanism used in the AK-47. Kalashnikov kept the lockup geometry identical, ensuring parts interchangeability. The bolt carrier, and recoil spring from an AK would function in an RPK and vice versa. This meant that a unit carrying both could exchange parts in the field if needed. The trigger group allowed for different modes of operation, controlled by a selector lever. In the RPK, the automatic setting became the primary mode, its reason for existing, but the mechanical components were identical to the AK. The hammer, trigger, and internal components all transferred directly. No technician trained on AK-47 maintenance could service an RPK without learning new procedures. The heavier barrel was the most significant engineering change. Kalashnikov increased the barrel profile, making it thicker throughout its length to absorb and dissipate heat. During sustained automatic use, a rifle barrel could reach extreme temperatures, causing warping and accuracy loss. The RPK's barrel was designed to handle this thermal load without requiring a quick change mechanism. This was a deliberate trade-off. Western designs used quick-change barrels, allowing an overheated barrel to be swapped with a cool one in seconds. But those systems required precise tolerances, additional training, and extra components in the supply chain. Kalashnikov's solution was simpler: make the barrel robust enough that changing it wasn't necessary during normal operations. If it eventually wore out, it could be replaced by a technician using basic tools. The sighting system extended the rear sight to 1,000 meters, reflecting the RPK's longer effective range. The front sight remained a simple post. No complex optics, no delicate mechanisms, just the minimum needed for practical accuracy at standard engagement distances. The bipod, though an addition, followed the same philosophy. It was a simple folding metal frame. It couldn't adjust for height, but it provided a stable platform. When not needed, it folded back against the barrel without interfering with the balance or handling. Every component decision served dual purposes: functional utility and industrial efficiency. The RPK worked because Kalashnikov understood that in mass production, every unique part was a multiplication of cost, training burden, and supply chain complexity. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing began at proving grounds outside Ijevsk in early 1961. The prototype RPKs would be subjected to trials that evaluated not just whether they functioned, but whether they functioned better than alternatives within the existing system. The competition wasn't against foreign equipment. It was against the question of whether this tool was necessary at all. Evaluators established test protocols that simulated squad roles. The RPKs would fire extended sequences to evaluate thermal management. They would be exposed to dust, mud, and temperature extremes to verify reliability. They would be disassembled and reassembled by personnel to assess maintainability. And crucially, they would be evaluated for parts commonality with existing AK-47 inventory. The first tests focused on sustained capability. Evaluators loaded 40-round magazines and fired continuous sequences, measuring temperature, accuracy loss, and failure rates. The RPK's heavier barrel performed as designed, maintaining acceptable accuracy through multiple magazines while the metal grew hot enough to discolor. Unlike standard barrels that would warp under similar stress, the RPK's geometry distributed thermal expansion evenly. But problems emerged. The initial wooden stock design showed charring near the receiver after extended use. Kalashnikov modified the stock profile, adding an air gap between wood and metal to create insulation. The bipod's attachment point needed reinforcement. The weight of sustained use was creating stress cracks. He redesigned the mounting bracket, distributing force across a wider surface area. Magazine feeding required attention. The 40-round magazine's spring tension needed calibration. Too weak, and it wouldn't feed reliably. Too strong, and loading became difficult. Kalashnikov tested multiple configurations until finding the balance between reliability and practical field use. The 75-round drum magazine presented unique challenges. Its rotational mechanism was more complex than the simple spring-loaded box magazines. In dusty conditions, the rotating mechanism sometimes jammed. Kalashnikov simplified the internal geometry and increased tolerances, prioritizing reliability over maximum capacity. The final drum design held 75 rounds but could function even when contaminated with sand. Cold weather testing in Siberian conditions revealed an advantage of the fixed wooden stock. While metal-stocked equipment became painfully cold to handle, the RPK's wood insulated the operator. But the cold also stiffened lubricants. Kalashnikov specified lighter oil formulations and recommended minimal lubrication in Arctic conditions. The equipment's loose tolerances allowed it to function dry if necessary. Evaluators conducted comparison tests with captured Western light automatic weapons. The RPK couldn't match the sustained rate of belt-fed systems, but it could match their practical accuracy at squad distances. More importantly, it could be maintained by soldiers with basic training. while complex belt-fed systems required specialist knowledge. The final evaluation criterion was the one Kalashnikov had designed for from the beginning: logistics integration. Evaluators confirmed that 80% of RPK components were identical to AK-47 parts. A squad could carry one RPK and multiple AKs, sharing magazines and ammunition freely. If the RPK failed, parts from an AK could repair it. The systems weren't just compatible, they were mutually supporting. In late 1961, the administration approved the RPK for service. Not because it was the most advanced equipment available, but because it was the most integrated tool for the existing doctrine and infrastructure. The final curiosity of the RPK wasn't revealed in its performance specifications or firing tests. It was revealed in a logistics report compiled by planners in 1962. The document detailed the industrial and supply chain implications of the RPK's adoption, and the numbers told a story that Kalashnikov had designed for from the beginning. Approximately 80% of the RPK's components were identical to the AKM, the modernized AK-47. This wasn't coincidence, it was the core design principle. The receiver, bolt carrier, gas piston, trigger group, safety selector, magazine catch, and recoil spring were completely interchangeable between the two tools. Even the furniture, handguards, and pistol grip was identical on early models. The implications were profound. Factories producing AKMs could manufacture RPKs on the same production lines with minimal retooling. The only unique components requiring dedicated manufacturing were the longer barrel, the reinforced receiver using the same stamping dies with minor modifications, the fixed stock, and the bipod. Everything else already existed in production. For supply chains, this meant the RPK created almost no additional burden. Ammunition was identical. 7.62 Kak 39mm rounds fed both. Cleaning kits, spare parts, tools, and maintenance equipment were shared. A unit technician supporting a group of AKs and one RPK per squad needed to stock only a handful of RPK-specific parts: barrels, stocks, and bipods. Everything else was already in inventory. For training, the integration was equally significant. Personnel trained on the AK platform could transition to the RPK in hours rather than weeks. Disassembly, cleaning, and basic maintenance procedures were identical. The mechanical operation was the same. The only new skills were employing the bipod effectively and managing sustained fire to prevent overheating. This integration principle extended to tactical doctrine. Infantry squads were built around the Kalashnikov platform. Every member carried an AK or an RPK. When a squad moved, every tool shared the same manual of arms. When they faced losses, equipment and ammunition could be redistributed without compatibility concerns. When they needed suppressive fire, the RPK operator could pass magazines to others or receive magazines from them interchangeably. Kalashnikov had achieved something subtle but strategically powerful. He had created a system that scaled. A nation could arm millions with AKs, then add RPKs to provide squad-level capability without fundamentally disrupting the industrial and logistics infrastructure already in place. The cost per unit was only marginally higher than an AK because most components were already being produced at mass scale. This was the gamble that defined the RPK's success. Kalashnikov bet that integration mattered more than optimization. A dedicated automatic weapon with a quick-change barrel and belt feed might perform better in theoretical specifications. But one that shared 80% of its parts with the standard rifle would perform better in the real world of limited budgets, large armies, and supply chains stretching across continents. The final curiosity was that the RPK succeeded precisely because Kalashnikov resisted the urge to innovate where innovation wasn't needed. He understood that in engineering, elegance isn't about sophistication. It's about finding the simplest solution that satisfies all constraints simultaneously. The RPK worked because it was almost an AK-47, and that almost was exactly calibrated to fill a doctrinal gap without creating a logistics burden. The RPK entered service in 1961 and remained in use for over 3 decades. Its longevity wasn't due to superior firepower or advanced features. It endured because it asked so little of the system it served. While other nations cycled through multiple generations of squad automatic equipment, each requiring new training and logistics, the RPK simply continued functioning as part of the Kalashnikov ecosystem. The design spread wherever influence extended. Many nations adopted it as standard. Regional movements received RPKs alongside AKs as aid. Licensed production began in numerous countries across Europe and Asia. Each manufacturer could produce RPKs using existing AK production tooling with minimal adaptation. The engineering philosophy embodied in the RPK influenced subsequent development. When Kalashnikov designed the AK-74 in the 1970s, he simultaneously developed the RPK-74, maintaining the same relationship between rifle and light automatic tool. The pattern repeated: shared components, minimal unique parts, complete logistics integration. The principle proved durable across caliber changes and doctrinal evolution. What the RPK represented was a particular approach to engineering, one that prioritized system integration over individual optimization. It emerged from constraints, industrial capacity, training timelines, supply chain realities, and tactical doctrine, emphasizing massed capability from dispersed units. Kalashnikov's insight was recognizing that these constraints weren't limitations to overcome, but parameters to satisfy. The design's legacy extended beyond its direct use. It demonstrated that interoperability and maintainability could be designed into equipment at the fundamental level, not added as afterthoughts. The principle of platform families, where rifles and automatic tools share core components, became standard practice in small arms development worldwide. Modern analysts studying the RPK often focus on what it lacked: no quick-change barrel, no belt feed, limited sustained capacity compared to dedicated designs. But this analysis misses the strategic dimension. The RPK didn't exist in isolation. It existed as part of a system that armed millions across dozens of countries. Its value wasn't in its individual specifications, but in its relationship to everything around it. Kalashnikov once remarked that the best tool was the one a person could trust completely. For the RPK, trust came from familiarity. Someone trained on an AK knew the RPK instinctively. A technician could maintain it with existing knowledge and tools. A logistics officer could supply it through established channels. This cumulative effect, this seamless integration, made the equipment far more valuable than its technical specifications suggested. The RPK worked because Mikhail Kalashnikov understood a fundamental principle of engineering. Complexity has costs that extend far beyond the workshop. Every unique component is a training burden. Every specialized part is a supply chain vulnerability. Every proprietary mechanism is a maintenance challenge. The elegant solution isn't the most sophisticated. It's the one that achieves its purpose while minimizing demands on the larger system. In 1961, Kalashnikov looked at an AK-47 and asked, "What if we simply made it longer and heavier?" The question seemed almost naive, but it led to a tool that served effectively for decades, precisely because it was almost invisible within the system it supported. The RPK's legacy is proof that in engineering, sometimes the most radical innovation is knowing exactly when not to innovate. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.